You should see it all right now, right? The lead slide.
Yep, absolutely. Looks good.
Excellent. Okay. All right. Well, welcome everyone, to what I hope will be an interesting conversation, both about what climate and energy research is going on today, but also the kind of the pivotal role that California plays. And obviously, with the change on the Democratic side from President Biden to Vice President Harris as the nominee, and obviously Vice President Harris being from Oakland, I hope a number of the things I'll talk about will resonate even a bit more in terms of what are the lessons, what are the successes and some failings from California that are making their way to the national level. So again, I'm a professor at University of California, Berkeley. I'm in 3 different departments. My main one is called the Energy and Resources Group. I'm also in the Goldman School of Policy, and I'm a physicist. I work on clean energy, solar and wind and energy storage, but also on nuclear technologies. And so I'm also in the Department of Nuclear Engineering. And my laboratory is the Renewable and Appropriate Energy Lab. You can see it here. I have served in the federal government on a number of occasions, most recently in the Biden-Harris administration at USAID. You can see that in the upper right. But I've also served in the Obama-Biden administration and the Clinton administration in the past in different roles, mainly on the energy and development side of the equation. And if any of the things that I talk about you want to follow, both there's the website of my laboratory. Again, it's called RAEL, rael.berkeley.edu. And for those of you who still use Twitter, X, despite concerns about its owner, we try to post like once a day about the things we're doing in our group on Twitter and X. And so again, it's listed under my name, but feel free to join, follow, or comment. And there's a pretty lively conversation there about some of the things I'm going to talk about today. So I wanted to do 2 things to set the context. And again, if either of them are too fast or not making sense, just jump in or put a comment in the chat and I'll try to follow it. And so the first one I don't think is going to be a surprise to anybody, and that is that we are not on pace to meet our climate goals. And the globally agreed climate goal is that we should be a net zero carbon economy by about mid-century. And there's a lot of different ways to say that. The way it comes up most often, so called the Paris Climate Agreement, is that we need to be having only warmed the planet, and I say only in quotes, by about 1.5 degrees Celsius by 2050. Now, we've already warmed the planet by about 1.2 degrees over the last century and a half. And so there's not much room left. There's not much headroom left for us to get to. And in fact, if we look at the pace we're on overall, there's different ways to talk about it. But the climate acceptable pathways would be down here. So we would have reduced greenhouse gas emissions from about 50 gigatons a year down to close to zero. Doesn't have to be exactly zero. Close to zero would be okay because there's ways to absorb some carbon. We can talk about that at the very end if there's interest, but you need to be more or less zero. And so the original Paris goal was to be at 2 degrees warmer than what it should have been by mid-century. And successive meetings of the International Climate Group, something called the IPCC, have dropped that number to about 1.5 because the damages are so large. However, look at those little bars at the top, you can see that we're nowhere close. So if we just continue with business as usual, we would grow our emissions. They are slowing in growth rate, but that red line is the business as usual. If countries do what they say, and that's so-called the national defined contributions, kind of a nerdy title, what that means is that each country builds a plan and they have to stick to it. And that was in 2015 when the Paris conference happened, but countries have been upping their game, at least on paper. And so you see the current national defined contributions is that gray line. It's not clear many countries are on that path, but you can see it's getting closer to where we need to go. But the challenge is we are not making significant progress on that. And by say that, I say, why the climate crisis? Why are we so worried about it? Hopefully you see it every day. Californians are kind of more aware than most with the fires that we see, with the changes in ecosystems. And one way to look at how different the world is now than in the past is just to look at this annual sea surface temperature record. And if you go back to some of the earlier records in the 1970s in blue, the 1990s in light blue, the 2000s in white, and where we are today, where you can see, if you look at the surface temperature of the ocean, it is not only higher than it's been in the 70s, that's obvious from the graph, but 2023 and now into 2024 is even worse. And it's worse not just linearly, things are taking off. And you can see from this graph that goes through July of last year, kind of 1 year ago today, that we are jumping into uncharted territory. And one of the reasons why this record of sea surface temperature is so useful is that you all know that the ocean is essentially a big heat absorber. And so when the temperature of the ocean is going up, that's a huge sign that things are on a, I don't want to say irreversible path, but the ocean warms much more slowly than the air. And so that's showing you how dramatically different we are than where we could be, should be, and need to be. So one way to think about that in terms of my lifetime versus your lifetimes is this kind of very famous figure that's in the latest global climate report. And this shows that someone born, I wasn't born in 1950 quite, but I was born in the next decade, the 1960s, that a 70-year-old person today, born in 1950, most of their life experience is in the period of little warming. Someone born in 1980, before most of your time, again, in their 40s today, they're seeing more of this later period. And someone just born in 2020, well, their life experience is going to be entirely in this warmed world. And there's lots of reasons why this is important. I mean, one reason to think about it is that our elected leaders tend to be in this older group. And so they are not used to the world we're moving into. You guys, I assume born roughly around 2000, in a very different state of mind about climate. And this is one reason why the politics of climate, not just the science, are so complicated, because older people tend to be more conservative and older people are not used to the world we're moving into. So you just want to keep that in mind when you try to understand different perspectives that you'll see out there. Another way to think about this is that 2-degree target that we had back in 2015, a way long time ago in 2015, was going to lead to a whole range of damages, from extreme heat waves to ice-free Arctic, to changes in species biodiversity, to coral reef bleaching, etc. And when we look at the difference between what was the target back in 2015, 2 degrees warming, limiting it to that, or the current target that's been adopted but is not being acted on, 1.5, you can see that the damages would be dramatically less if we could keep the warming lower. So it just kind of keeps, it keeps in mind, and hopefully it keeps in mind for you how critical it is to kind of think about these lower targets, even if we're not making progress. More or less, everything is twice as bad if we warm to 2 degrees versus if we can limit warming to 1.5. And that's why what I'll talk about with some of the more aggressive strategies, I hope make sense. This isn't the only bad news out there. When we look at things like this was New York City in May of last year. 2 days later, during the fires in Ontario, New York City looked like this. And of course, that looks pretty similar to the world that, at least in science fiction, we were talking about for 2050. So we are getting to these bad climate targets earlier. And this is only thinking about the world from a climate basis. I'm hoping that a lot of you are thinking in the back of your minds, well, I know climate's bad, warming is bad, fires are bad, but what does it mean for me or people I know personally? And so the way we think about that is to have a whole set of indicators. These are the United Nations agreed upon Sustainable Development Goals, or the SDGs. Each one, I hope, seems pretty obvious, and each one of these goals are things that the nations at the UN have agreed we need to make dramatic progress by 2030. So no poverty by 2030. That sounds a bit pie in the sky, but is reasonable. Removing hunger. And I'm going to focus on SDG number 7, and that is to change the world's energy system so that everyone has access to affordable and clean energy by 2030. And this is a goal that's achievable. We have about 750 million people on the planet, 750 million people, who don't have access to modern energy today. Lots of the others are really important: gender equality, education, clean water access, protecting life. I hope these all kind of make intuitive sense. But again, what I'll talk about today will mainly be the climate story, both California to Washington, D.C., and then some of the impacts and opportunities elsewhere in the world, like where I work mainly in sub-Saharan Africa or Indonesia, where I just came back from a couple of days ago. So that's kind of the longish introduction to what we're going to talk about. And we're not on pace to meet those Sustainable Development Goals. Only about 15% of them are we on track, and some of them are going backwards. So that is a bad picture of all these different goals. And it highlights that our climate story is bad. If that wasn't depressing enough, our sustainable development story is bad as well. And again, I'm going to talk about clean energy going forward and leveraging some of the experiences in California and how they have played out elsewhere. And so after that kind of bit of long introduction, let me jump in and highlight the other, I would say, big ticket feature. And that is the other part of the climate story is one about justice or injustice. And when we look at the richest 1% of the world's population, they contribute about 15% of global greenhouse gas emissions. The richest 10% are over half, 52% of greenhouse gas emissions. And the poorest half of the planet contribute less than 10%, 7%. So hopefully that really puts it in context in terms of the numbers. And if you just go downtown Oakland, you can see this large billboard that's hanging, and it's really instructive. This is hanging downtown Oakland, right by Lake Merritt, and it shows that the average life expectancy, if you live in a West Oakland zip code, 94621, is 74 years. But if you look at people who live in the Oakland Hills, it's a full decade longer. And so environmental, racial, gender, justice, injustice comes up in lots of different ways. And in many ways, that's the most important lesson here. So why talk about that in the context of climate? Well, the tech story is the dominant story in Silicon Valley. You know, when you look around, you look at the massive numbers of companies. They used to be almost all IT, computer science, clean tech companies. Now there's a huge range of clean energy companies that are part of that Silicon Valley story. And what it leads to is what I would call the Silicon Valley agenda. And that is, if you have a problem, whether it's lack of social media, whether it's lack of connectivity, whether it's lack of clean energy, you tend to focus on it in terms of the tech-based solutions. There's a famous book arguing that Silicon Valley is a place where that story really comes to bear, called Regional Advantage. And just to kind of put another version, this is a book by John Doerr, one of the famous Silicon Valley investors, saying we need to do things at speed and scale to solve the climate problem. If I take a super tech nerdy version, this is a graph which I hope is going to look way too complicated for you. But what it actually shows is what's the maximum efficiency of solar cells going back to the 1970s. And what you see in each line, each color represents a different kind of solar cell. The classic ones we think about are the purple and the blue at the top. And you can see that the maximum efficiencies have more or less been ramping up linearly. There's bumps and jumps. Different companies are involved, different universities. You can see the names scattered in there. But they're more or less linearly improving from efficiencies of about 30% of turning sunlight into energy, or 20% back in the 1970s. And today, some of the best solar cells have efficiencies in the 40s. And most of the commercial cells we see today on rooftops are in the mid-20s to low 30% range. That's a super tech nerdy version. There's obviously lots of things going on down here. You can see the red. They're ramping up more quickly, but they're newer. But that approach to thinking that we can tech our way out is a start, but it's definitely not what I'm going to argue is the way we need to get there. And that's saying a lot because I'm a physicist. This is kind of the world I grew up thinking about. The real story is graphed a little differently, and these are called learning curves. These show the price over time for wind. LCOE means least cost of energy, levelized cost of energy. So wind has dropped in price by about 50% over the last decade, solar by 90%, and batteries by 90%. So there's a wonderful tech story. And what that means is that today, 2024, it's actually now cheaper to build a new renewable energy power plant than it is to operate an existing fossil plant. And that is a world that's totally different from a decade ago. It's kind of an amazing step forward. So these learning curves can be plotted just like you see here. This is price over time, or kind of a cool, different way to think about them on the tech edge is to think about it this way. This is the same data for solar cells, but plotted kind of engineer nerdy way. So what you now see is the price on the vertical axis in log units, so order of magnitude units. But on the horizontal axis, that's not time anymore. That's total global production in orders of magnitude, gigawatts, 10 to the 9th watts of energy. And so this plot actually tells you a huge amount about what's going on. Mathematically, what we're writing is that the cost at some time like 2024 versus the cost in some other time, say 1978, is actually mathematically a function of the volume of sales, cumulative production. So the volume in 2024 versus the volume in 1978, and it's raised to a negative exponent. That's this negative curve. Now, that's a lot of math to just say that the price is falling. So the reason why I'm highlighting this is because what this graph says is that anytime you see a straight line in log space, that's called a power law. And that means that the rate of change is equal to the slope of that line. The slope of this line, the coefficient B, is 20%. So what that says is that since 1978, we've seen pretty steady, there's a few bumps and dips, but what we've seen is that the price of solar has dropped by 20% every time we doubled the amount of solar cells that are manufactured and deployed. This has got different names. It's called Moore's Law. That's a Silicon Valley name for it. It's also called Swanson's Law. But that's a way to think about what you get by making technologies cheaper. So right now, the world is building its first huge, I guess, pun intended, wave of new offshore wind turbines. They are as big as some of our iconic San Francisco buildings. And the reason why this is so interesting is if you do offshore wind turbines, they can be bigger, they can be built more quickly if you have the right equipment, and they can also be built in areas where we don't have to worry about them directly impacting people's homes and communities. So there are some interesting new things going on that kind of highlight the story. And if you want to look back and say, well, what is the carbon footprint of my neighborhood in San Francisco, in New York City, and wherever else? This is a calculator that we built. The New York Times reported on it. You can just Google the climate impact of your neighborhood. And this kind of shows you the carbon impact. And if you look at all these cities, what you see is that the greenhouse gas emissions, not directly from each home, but associated with the energy you buy, the goods you buy, show that city after city, the urban core tends to be lower carbon than does the suburbs. And that should make sense. People in the suburbs drive more, packages have longer to be delivered to their homes using more fuel, although Amazon is sort of switching over to electric vehicles. And people in the urban cores where property values are higher, costs are higher, tend to have smaller homes. So cities are both a problem. They're a source of us doing lots of things, but they're also a place where maybe we can learn to live a bit more within our means. And so there's some interesting ways to think about the data out there. And one of the things that my lab has done is to try to do this kind of analysis, but then really focus on what are the opportunities. Why is it that in California, the poorer you are, the farther you have to drive to get to school, to work, etc.? And can we use things like policies at electric vehicle companies or at Uber and Lyft and others to try to push for more clean energy vehicles in the market? So again, that's the kind of thing that I do a lot. Here's some work we're doing with a friend of mine, a professor used to be at UC Santa Cruz, now he's at USC, highlighting that California's own goal to be a climate leader by 2045 isn't good enough. We could be going faster. So let me spend my last a bit of time, the last 5 minutes, and I'll open up for Q&A, highlighting the story of California and why it matters so much for the federal level. And I see some of the questions coming in, and we'll get to some of those. So California's goal for its economy in 2010 was to be 20% powered by renewable energy, solar, wind, biomass energy, if it's sustainable, geothermal energy, meaning energy from hot, dry rocks. In California, we don't count nuclear, and we don't count large hydro, big dams, as renewables because of the environmental impact. We missed our 2010 goal. We didn't get there until 2013, so that sounded pretty bad. But our 2020 goal of being 1/3, 33% powered by renewables, we met that in 2017. So in 4 years, we went from behind schedule to ahead of schedule by deploying more and more clean energy in the state, both big solar and wind farms in the deserts, rooftop solar like many homes, including mine, have. And our goal for 2030 was to be 50% powered by clean energy. But because we did so well on our 2020 goal, we've increased that to 60%. California's goal on paper is to be carbon neutral, meaning no more fossil fuel use that we don't find a way to offset, either in stationary power or in mobile vehicles. Now, that's the law, and you saw that in that op-ed I just flashed up on the screen before. We've been arguing California can and should get there much earlier, and it's because of those learning curves and the rapid changes I've shown you. There's another part of California's cap and trade law that I want to highlight, and it's what I would call, or what we now call, the just energy transition. So California has a tax on pollution, meaning if you're a big company and you emit greenhouse gases, particularly carbon dioxide, but also methane, carbon dioxide CO2, methane CH4, those are both potent greenhouse gases. If you're a big emitter, you pay to do that. You can either clean up your company, that's the cap, or you can trade, you can buy the rights. And there are some worries about buying your rights because that sort of means that you are taking advantage of the market, but that's part of the rules that we currently allow. But what California has done is to say that 35% of the revenues from our cap and trade system, currently there's about $11–12 billion traded in that cap and trade system, must be spent on underserved, marginalized, overpolluted communities, so-called fence line or environmentally justice communities. That piece of California's climate law is in many ways the most interesting feature. It's the one that's been the biggest change from business as usual. And California has been doing pretty well in this regard. California, earlier this year, was able to, for a couple hours, meet 95% of our energy needs with clean energy. And here's a graph just showing during that day, this is a day in April, where the amount of clean energy in green ramped up and ramped up and ramped up. The amount of natural gas, methane, CH4, went down. We were able to export energy, went from importing to exporting. And the amount of hydro we used goes to zero. And I'll get to question 5, is cap and trade truly effective, in a bit. And just a preview, you're probably not going to be surprised at the answer. So that's where we are in terms of making changes. And what that's meant is that California has been able to change its energy system pretty dramatically. We still have some issues. California still needs to get rid of fossil gas, natural gas. So here is a plot showing where we were in 2021. This is a plot from midnight to the end of the day. And you can see the amount of wind is kind of sort of steady. Hydropower, we're able to ramp down the amount we use during the day because of new technologies. Nuclear and geothermal are kind of flat. They're just always on. And you can see the amount we import in the end of the day is still there, but in the middle of the day, we were beginning to export. That's 2021. And solar is the biggest chunk of that. Just 3 years later, we are still looking kind of similar, except that we've added so much energy storage. We're basically using it to deal with the wings of the curve when we used to import, when that peak demand happens in the late evening, when some businesses are still on and people are going home. And you can see that by adding more and more storage, we flattened it out so that we're importing only at night somewhat, and in the evenings, we're able to export in the middle of the day like you've seen, and solar and wind are becoming our biggest sources of supply. So that is a dramatic change. And what it does mean is that we're able to find new ways to meet our energy demands. And the question, I'll just wrap it up here, is how are we able to kind of find ways to sort of play that into the market? So here's a picture of California just back in March. And the price of energy, because of all of this locally generated clean energy across Western US, went negative, meaning there was so much clean energy and we still had legacy contracts with old nuclear and gas plants that the price of power went negative. Texas, oil and gas dominated Texas, went to zero price of energy because they've added so much energy and storage. They've added more renewable energy than we have. And only in the East is the price of power still positive. So we are seeing some dramatic changes. And what that means is that if we think about that curve during the day, it's actually got a name. It's the duck curve. You can see that flat demand at night. And then as we add more and more renewables year after year, we go from a place where there wasn't much 10 years ago to now where we're exporting power. But then we still have to deal with this neck of the duck at the end of the day. But these prices coming down mean that we now have all of this, I don't want to call it excess, but all of this energy that we can really reallocate. And so making, powering up our electric vehicles, or putting that energy into making green hydrogen, we can store hydrogen, or finding ways to use that energy to charge up batteries, are all things that we can do. And they're all part of what's going on at the federal level. So let me just kind of wrap up with a version of California's experiences were critical in what happened 2 years ago in the House and the Senate passing the so-called Inflation Reduction Act. And the Inflation Reduction Act is the biggest ever investment in clean energy in the United States. What's interesting is that it has subsidies for solar and wind power. It removes some subsidies, but not all, for fossil fuel power. And it also invests money in the largest single chunk of the Inflation Reduction Act. 60 billion out of the 360 billion goes to underserved, marginalized, we call so environmental justice communities. So this Inflation Reduction Act is expected to dramatically bring down our pollution mix from that current policy line to one where we will drop even further on emissions. And obviously what happens in this next election is going to be critical to that process overall. But I just want to, to highlight before you move into the Q&A, both the questions you have and some that will come up, this overall push towards learning from what's going on in California. Not everything is good. The question from AS here is about AI and machine learning and the energy demands for data servers and other types of big new energy consumers. But all of these are parts of the kind of the process moving forward. So let me end the slide part. I see we have, call it 5, 6, 7 questions, but I'll drop off of screen sharing so we can see each other. And let me try to answer those questions and then all the others that come up as well. I don't think I stopped. There we go. Stop sharing. Let me jump into the chat, and I'll try to do this quickly because I know we've got 5 minutes, but then see which other ones you put in there. So what are the environmental impacts of electric vehicles? So the first thing is that no matter how you slice it, electric vehicles are far, far better than gas-powered vehicles. Sometimes you hear some people trying to push back on that, saying, oh, no, they're not such a great benefit. They really are. There's no question. A gas-powered vehicle gets what, 30 to 40 miles a gallon at most. An electric vehicle can get 150, 200, 300 miles per gallon. And most of those emissions have to do with what the question's about. We mine different materials, cobalt, tungsten, manganese that go into batteries. Even with those negatives, these batteries are far better. So electric vehicles, far, far superior to gas-powered vehicles, not only in terms of their mileage, but the cost to drive is dramatically less. It's often 20 to 30% the cost per mile. So if 100% is a gas-powered vehicle, it's often 20 or 30% of that in total that you would need to do a electric vehicle. We do need to get better at recycling, but most of our recycling challenges actually have to do with materials in our computers, our laptops, our cell phones. The amount of energy in batteries is for electric vehicles, for clean energy systems is there, but it's small compared to the amount that we currently have in these other uses. But it will rise, and it's one that we're going to have to be very serious about. So question 2, how can homeowners incentivize the process? Well, there's many ways, but maybe the first is a very California story, and that is California first gave subsidies for energy efficiency, more efficient light bulbs, refrigerators, and going forward, California then had subsidies for solar panels. Those subsidies have been ended because solar panels are now so inexpensive. But if you install batteries, you get a subsidy for that because we're trying to build that out. And so all of those are sort of parts of what governments can do. This Inflation Reduction Act is kind of a national government version of the process. And then nuclear, question 3, how about the risks of nuclear? So I'm a professor of nuclear engineering, but nuclear has a pretty challenging road ahead of it. A lot of ways to think about it. We've seen what happened with the Fukushima Daiichi accident. Historically, we saw the US 3 Mile Island accident, and we've seen accidents at so other places, Chernobyl and others. And so I guess the way I would think about it is as follows. There's 420 nuclear reactors in the world today. 100 of them are in the US, 60 in France, the rest are scattered around. Each of those 420 reactors must be shut down by mid-century. That's just the end of their normal life. There'll be some life extensions and things. California has 1 nuclear reactor. It was supposed to close in 2015. We've given it a life extension up until 2030, but then it's going to have to close. Even if nuclear has a wonderful, amazing future where we build lots of nuclear plants and there's no accidents, those are both big issues, and there's no big cost for risk, those are another big issue. It will be hard-pressed for the world's nuclear industry to even rebuild all of those 420 plants. So in one view, a really, really good future for nuclear would just to hold its current market share. And nuclear power is about 19% of US energy, and it's about 10% of global energy. Now, if you're a super proponent of nuclear, you can say, well, that's the past, the future could be something else. That's true. But usually in the world of energy, the past is a pretty good view of what's going forward. And the other problem that nuclear faces is that it is just too expensive compared to solar and wind and batteries. Now, that doesn't mean there isn't a role for it. I would love to have nuclear have a big role. I myself am part of a fusion energy company, not fission, not uranium and plutonium, but using hydrogen. So I'm very excited that the future could be bright, but it's got a long way to go. Question 4, in what ways can undergraduate students in energy prepare for internships in the application cycle? So the good news is that it does not matter what your major is. You're an English major, you're an econ major, you're a rhetoric major, you're a history major, you're an energy engineering major like we have at Berkeley. All of these jobs are needed and valued in the field. And so the biggest way I would say if you're an undergraduate is to take a course. Almost every university now has kind of an intro to energy systems class. Here at UC Berkeley, I offer a class called Energy and Society that is a big introductory class to energy issues. And it's a kind of a big starting ground to get an understanding of all the technologies. In fact, many of the slides that you saw, I use in those courses. The other way is that if you're in the Bay Area, it's a particularly excellent area to get involved because there are so many clean energy companies in San Francisco. Tesla and Enphase and Enlighten Energy and Breakthrough Energy. There's energy company after energy company, and finding them isn't that hard if you kind of go on to clean tech sources. I don't want to make it purely political, but one of the groups that I'm involved with was first called Clean Tech for Obama. Then it was renamed Clean Tech for Biden. I suspect it's about to get a new name for Vice President Harris. But it's a Bay Area-based group that brings together energy leaders from around the Bay Area and around the planet to kind of get people in place, in jobs, in positions, whether it's on the tech, energy, engineering side, software side, economics, policy. These are all kind of opportunities to kind of engage in these areas. So I've gone a little bit over. I know we have a slight bit of some, and why don't I ask people just to jump in with questions, audio, because answering written questions still feels like me just talking. So why don't you guys jump in and we'll do like one or two and then end so we don't go too late.
Yeah, so we had a few asking about cap and trade actually that were private message to me. So yeah, the question is cap and trade truly effective?
Yeah, so nothing is purely effective. There are three distinct policies that have been passed around the world. In California, we have this cap and trade, which means we have a market mechanism. There's a cap on overall emissions. Right now, only big companies are required to reduce their emissions based on it. And what our cap and trade says is that if you emit more than 25,000 pounds of pollutants a year, you can either choose to decarbonize by investing in renewables or recycling or something, or you can go onto the market and buy a permit to pollute. Now, there's a capitalist versus socialist kind of perspective there, but right now the price of that permit in California is about $30 per ton of pollution you put into the air. In theory, all that money goes to another company or another group that can do it more effectively. So many people say cap and trade is the least exciting, but the most pragmatic solution to pollution. Other groups say, no, we should have simply a tax. Anyone, any size who pollutes, you pay a tax. That sounds simpler and more egalitarian, but what it means in the end is that everyone has a reason to oppose it. Because even if you like the idea of going green, everyone sees, oh, this is going to tax me. So more places have cap and trade systems than have carbon taxes. And there's a third proposal that gets talked about all the time. No one has done it, but everyone seems to love it on paper. And that's called a cap and dividend. So there's an overall cap, and big companies pay, and that money goes into a pool, and some of that money gets used by the government to do research on clean energy or to incentivize projects, but the rest of it gets given back to consumers. So everyone gets a rebate check. In California, if you pay a utility bill, you actually get a rebate check. It's about $60 a quarter. It goes back to every ratepayer. And that's great. And the reason why I said that almost no one does this is because California's rebate program gets almost no press. Getting a $60 check is not trivial, but it's smaller than many people's utility bills. So it's a good idea that kind of gets swallowed up in the noise. And so cap and trade, carbon price, just carbon tax, or cap and dividend, money being given back to consumers, are the three models that are mainly in use today. And again, cap and trade is by far the most common of those. Maybe one more. How about that? Unless we're all out. Looks like we might be.
Might be good.
All set.
All
All right. So again, I put up in that slide our Twitter. It's just my name, Dan_Kammen, if you want to kind of comment or see some of the dialogue. And I do post job advertisements and internships and things. So hopefully that'll be useful for some of you as well. And again, thank you all for listening.
Yeah, thank you so much for your time, Professor. All right, have a great rest of your day.
Thanks a lot. Thank you all.